Let me start by welcoming everybody. Good afternoon. I'm David Tilbrook. I'm hosting this series of talks on behalf of the AIP. And I'd like to welcome you all to the third seminar of the AIP Theoretical Physics Seminar Series for 2021. I'd like to start, of course, by acknowledging the people of the Ngunnawal Nation on whose land we are located here at ANU, and also, of course, to traditional owners of lands all around Australia. We would like to pay our respects to their elders, past, present, and emerging. I also should acknowledge the organising committee for the series of talks, and especially Murray Batchelor, who in particular have volunteered their time to identify topics that are interesting and represent some of the important developments in the current state of theoretical physics. This is the third seminar in the series. The first two were given by talks by Professor Tracy Slattier from the Massachusetts Institute of Technology, who talked about the existence and properties of dark matter, particularly from a particle physics point of view. And the second seminar was given by Professor Raymond Volkas from the University of Melbourne on the recently announced result from the Fermilab G-2 experiment that seems to confirm the existence of the difference between the theoretically predicted magnetic moment of the muon and experimental data. And that, of course, has potential implications for the standard model. If you missed either of those talks or you'd like to watch them again, they're available on the AIP YouTube channel. The easiest way to find that is just do a search with your favorite search engine for Australian Institute of Physics YouTube. Use that as the search term. That'll take you straight to the AIP YouTube channel. Today's talk is by Professor Susan Coppersmith from the University of New South Wales on an equally interesting topic, that of quantum stochastic resonance. Professor Coppersmith is well known for her contributions to condensed matter physics, such as the developments of structures for quantum computing, particularly those, I believe, in silicon and silicon germanium heterostructures, and for the development of various methods for the robust fabrication of nanostructures, just to name a couple, just to name two of many areas of condensed stereo physics. She is a fellow of the Australian Academy of Science, the Australian Institute of Physics, the Royal Society of New South Wales, and the American Physical Society, just to name a few. As many of you may be aware, stochastic resonance is the phenomenon usually associated with nonlinear systems, whereby the response of a system, for example, to a periodic stimulus, can be enhanced by the presence of noise. And this phenomenon can be extended to quantum systems as well, as we will hear today. When I was working for CSIRO, I looked briefly into the possibility of using quantum stochastic resonance as a way to improve the sensitivity of squids without much success due to my own lack of knowledge of the subject, I think. But it has many potential applications, especially for quantum computing, for example. So I'm really looking forward to hearing more about this topic from an expert. If you have any questions that arise during the talk, please type them in the Q&A panel at the bottom of the Zoom window, and we'll answer those at the end of the talk. So without any further delay, over to you, please, Susan.
Okay, great, thank you. I also want to acknowledge the Bedegal people who are the owners of the land on which the UNSW campus in Sydney is located. So I'm going to talk about stochastic resonance, and I do have some information about the origin of stochastic resonance, which is really quite interesting, I think. And but before I get to that, let me just acknowledge the collaborators. I'm going to show you experiments from a group in at the University of Stuttgart, led by Sebastian Loth. And the experiments were all done before I got involved, and there's sort of a story behind that. And the work that I've done was funded by Fleet. And actually, I would never have found out about it except for Fleet, that I would not have found out about Sebastian's work. But I decided I'm sort of not doing, I have to somehow get into, I've got it. wait, I have to do annotate. Sorry, guys. You would think I could do this by now. Okay. So I know good pedagogical practice and whatnot. I should do the bottom line first and not tell you my life story, but this is a talk about my life story, and so I apologize. I hope my life story is not as boring as I fear it is, but I think it's interesting from the point of view of theory, because I'm really talking to a theoretical audience, and to me this is like so exciting that you do something sort of taking concepts from one field, you apply them in another field, and I think that's one of the great value propositions of theory is seeing interesting concepts that can be adapted in new contexts that where they can have an impact. So that's thing number one. And thing number two is sort of a very true thing where I'm going to show you a bunch of work I did in the 1990s before many of you were born, I'm sure. And it was just a paper that like dropped into the abyss. And it turns out it's relevant now. So it's like, eat well, exercise, and get sleep and all that stuff. And maybe like something like this will happen to you, where like someone will notice something you did. We'll do work where work you did a long time ago is actually relevant. So I have to tell it to you in historical order, just because I can't help but think about it that way. Okay, so here's the outline. So again, like as Dr. Dobrik said, or Professor Dobrik said, stochastic resonance is an interesting concept that was developed in the context of nonlinear dynamics in the early 80s. And I'll give you just a brief introduction of the idea behind it. And then I can't help but tell you about the work we did in the 90s, where we first realized that this concept, which has been applied to many, many nonlinear systems in the classical domain, could in a fairly straightforward way be extended to the quantum domain. There are just a couple little ideas you had to have in order to realize that the idea, the concept really carried through in a pretty straightforward way. But also when we were in the 90s, we were able to work out quite a lot of the theory that we realized we could really calculate in a more general context and do really analytic work that, we could, if you told us, you'll see in the things described with transition rates and sort of any arbitrary dependence of transition rates, we can compute sort of anything an experimentalist might want to know. And nobody cared, and no experiment was done. And then last year during pandemic, I'm sure you've had the same thing where you're like logging into seminars from all over. And this was a seminar based in Finland, but Sebastian Lotz was talking, and he was talking about his experiments. And they had done this. And like, I'm like, well, they said, well, wouldn't it be great if someone could calculate? You'll see what we calculated. Wouldn't it be great if someone could calculate this quantity? It's like, I know how to do that. It was so exciting. Anyway, but on top of being able to, sort of help them analyze their experiments and really characterize stochastic resonance and sort of know precisely, like what assumptions are involved in the fit to the experiment. It also provides an avenue for moving forward and now they're pushing into regimes where the assumptions behind the model, I'm going to show you, may fail, but studying that failure is very useful because everything theoretical is sort of exact, and so any failure to agree with data is a failure of the fundamental assumptions, and so we're actually pretty excited about moving forward. Okay, so hopefully soon. So as you see, it's been quite a gap between steps, and hopefully the next steps will be less of a gap. Okay, so here's the introduction. I assume not all of you know, because again, this is, it's not such a well-known concept. So the original motivation was, oh, I think I forgot Parisi on this reference, I'm so sorry. Okay, the original motivation was because of the near periodicity of the ice ages. And again, we're hoping we get one again at some level, right? But if you look in the literature, and this is actually from a U.S. National Academy report on climate change from 1975, there are various things you can measure on different time scales. And so this reference is actually a guy who's sort of summarizing all the different periodic variabilities that have been, sort of hypothesized in climate. And here, what it's a study of oxygen isotope content of fossil plankton, but that's supposed to be correlated with the temperature. And basically you're looking at the variability of this. And so you're looking at variations in temperature over, very long timescales. Again, you're looking in the fossil record. And what you see is this, huge, really pretty substantial peak, because they use 0 as the axis, as the bottom and everything, right? A really substantial peak at a periodicity of about 100,000 years. And it was noticed because then you look at what are all the variables, astronomical variables, and one of them is the eccentricity of the Earth's orbit varies on a scale of about 100,000 years, very close. And where the origin of that is just the motion of the planets, like the big planets pull, more, and so there's a slight variation in eccentricity of the orbit, and that is the time scale. But you can do an estimate, and the perturbation is just like you're a little closer to the sun, so you get more radiation. But then the eccentricity, you're farther away, you get less, and so it's quite a small effect, okay? But it's just from the radiation from the sun, because the distance is a little different. There is a small change in the amount of sunlight hitting the Earth with this period. But the perturbation, when you estimate it, is I think it's like 2 orders of magnitude too small. Somewhere between, it's not crazy small, but like between 1 and 2 orders of magnitude too small to explain the effect. And again, the average change in temperature during an ice age compared to a non-ice age, ignoring global warming for now, is about 10 Kelvin. And when you do the estimate from just the radiation hitting the Earth, you get some 0.3 degrees or some fraction of a degree. Okay, so it's quite a significant discrepancy, but not ridiculously too small. So they thought, well, maybe there's some way where you could get some enhancement to the perturbation, some way of amplifying a perturbation. And they thought of this idea that maybe noise can amplify the effects of a small perturbation. And that is what stochastic resonance is. So it's like it's sort of resonance in the sense that there's an optimal amount of noise to get the largest response to a given drive. Okay. And so the idea is that the Earth's climate is, you model as a particle, a system, a degree of freedom and a double well potential, and this side is the cold side during the ice age, and then there's a hot side, which hopefully is an actual side where you don't run off to infinity. Let us pray. But there's a hot side, and then you're going back and forth, and then there's a small perturbation that there's you're more likely to be cold because when there's a little less radiation, and then you go back and then you oscillate. Now here there's a little more radiation, so there's a periodic driving on the system. Okay, and so just to let you know, that will be the last I have to say about climate change, because after that people just sort of study this concept of, well, what happens when you add noise to a periodically driven 2-state system. Okay, and so basically, these are numerical simulations, and it's a particle in a double well potential, and then they move that potential back and forth. And this is the driving, and what you see is that at low temperature, what happens is they made it moderate, but they made it where you would just get stuck in one state, and certainly on the period of the drive, like nothing would happen, because you would just be stuck in this well and you wouldn't get out because you just didn't have enough, you couldn't get activated over that barrier. And at high temperature, what happens is you go back and forth, and the transition rate is much faster than the period of the drive, and the energy, from the perturbation is small compared to the thermal kicks are bigger than the deterministic kicks, and so it just doesn't care about this small drive. Okay, but in between, then you get a situation where the well moves over, and then particle jumps, and then, you know, it goes back and it jumps the other way, and you can get, you know, quite a strong synchronization of the response to the drive. Okay, and that is stochastic resonance, and there's, you know, and it's a you know, it's a simple model, but it's a, you know, very well defined model that you can study and, you know, make progress on. Now, in terms of like what people then you say, okay, we want to quantify this, and there's sort of two main ways that people have quantified it. And the original one, which really was motivated by this original idea of the ice ages, is, you know, the signal to noise ratio, like, you know, what's the probability you get over there, and that, you know, you have you know, what's the response to the drive, and that's measured by there's a component that's at the Fourier component of the drive. That's a signal, and then of course there's a broad background because it's a stochastic process, and then you just take the ratio of, you know, the area in the peak in the delta function and the area in the broad in the broadband piece, and that's the signal to noise ratio. And you know, very early experiment by Fove and Heslow, you know, this is now 3 different amplitudes, and you see that, you know, there's a you know, for the parameters of this experiment, there's you know, a maximum, there's a peak in the signal to noise ratio at a characteristic noise amplitude. All right, and so that's one way it's characterized, and the other way, which is actually going to be more relevant to the experiment I'm going to show you, though they did do the first one also, but the second one is this one is the one that I'm going to focus on, is what's called the distribution of resonance times. And this you can you sort of look here, right? You know, you say, how long did I stay in that state? Okay. And again, this is half a period, right? Because you're in the left, you're in the right. If you're going back and forth and you're perfectly synchronized to the drive, this resonance time is half the period. Okay, but then what happens is that if you don't make it the first time, then you got to wait for the drive to come around again. And so that's why you get a distribution of these resonance times at peak, at half the drive frequency, 3/2 the drive, 3/2 times the period of the drive, etc. Okay, and so and this is actually the analog of what we're gonna look at today. But both of these are like perfectly valid ways to characterize. Okay, and then finally, all the work that we've done is based is sort of as follow up in some sense to a theory approach that was first written down by McNamara and Wiesenfeld. This again is a very famous stochastic resonance paper, where they just said, well, let's just put everything in terms of transition rate. So up till then, people had been doing sort of analog simulations and sort of, you know, solving differential equations with noise in them. But they said, well, look, we can just think about it in terms of transition rates. There's some probability that you go from the left to the right, and there's some probability that you go from the right to the left. And those probabilities depend on time. And that provides a really simple way of thinking about the problem. And then later on, when we did the actual work, this was the model that we used. But I introduced it at this point just because it's so much easier to talk about the rates, because they're very simple things to think about. Okay, so and so everything I've told you up till this point is people were thinking completely classically. Okay, and so if you have a classical model in this transition rate formalism, then it's just basically you're going over a barrier. You have activated excitation over this barrier, and the barrier has a height u, and then and essentially you have epsilon is you know, it goes up a little more, that you the point is that you go back and forth and there's detailed balance, and so the detailed balance is sort of here, right? That the probability of going to the left is a little more than the probability of going to the right, and these rates obey detailed balance. And again, what you're doing when you're driving is you're just modulating these rates, and you can modulate the rates either by changing the asymmetry or by changing the temperature. Okay. And but the other thing is that, again, up until that point, people had focused on the symmetric case where the energies of the two states were the same. And so so people hadn't really thought about what happens if you change the asymmetry in general. Okay, all right. Okay, so where's the stochastic resonance? Is that basically at low temperature you're stuck on one side and you never get activated, or you get activated only once in a blue moon. At high temperature, again, you just go back and forth so fast that it doesn't, and the detailed balance doesn't, it doesn't really care because the temperature's high, so it doesn't matter. It doesn't care which side it's on. But there is an intermediate temperature where you get a maximum response in the synchronization to the drive. So, so now, again, I'm sorry, I'm telling you about my youth. So again, in the 90s, Ritva Lofstedt and I asked the question of, well, can you generalize this concept to quantum systems? And in some sense, there are many. In some ways, there's good news, right? There are many quantum systems where transition rates are relevant, and there are many quantum systems in which you can modulate your transition rates, that you can vary them and do something. But on the other hand, everything in stochastic resonance, you had this picture of you had to go over this barrier, and there was a very strong dependence because of the activation over the barrier, and quantum mechanically. Typically one of the rates, it's a quantum mechanical tunneling, so it doesn't depend on temperature. So you don't have the situation where, you have to go over this barrier, but rather you have a tunneling rate that tends to go to some constant as temperature goes to zero. But the thing is, again, this is at some level, the only idea at that time was, the thing is that if you think about having an asymmetric system, then it's true your fast rate is constant as your temperature goes to zero, but your slow rate still obeys detailed balance, and so it does exponentially depend on temperature. And so you can modulate one of the rates. And so then you're just left with this question of, if you modulate one rate, can you still see stochastic resonance? And the answer is yes. And this is the work that I did with Ritva back in the 90s, where we realized that you modulate one rate, and it turns out that the phenomenology is not exactly the same, but it's really very similar. All right. So here's sort of the picture of of what's going on. Very similar to the classical case, only now instead of thinking about going over the barrier, I mean, you can go through, but you have to you have to sort of find the energy to go from the lower state to the upper state. You're parked in a situation with asymmetric rates, and again, if your temperature is really low compared to this energy difference, then this is epsilon, this is the asymmetry. If your temperature is really low, well, then you modulate you modulate it, but it doesn't matter. It's still much less than the temperature, so you never make it to the upper state. And it's just sort of a trivial fact that if you're stuck in the lower state, it doesn't matter what the transition rate from the upper guy is, because you're never there, so you never see it. Okay, so here nothing happens, and then if you're at high temperature, then again these rates obey detailed balance, and if epsilon divided by kT is small, they're basically equal, and they're equally occupied. Okay, but there's a intermediate value of the temperature where you get a big change when you modulate. Okay, now back then, again, we were thinking of a case where we had like a thermally controlled process, but then we wanted to quantify everything. And when we did that, it turned out that we were able to, I was gonna say this next, so sorry, this is skipping ahead. We were able to quantify it for arbitrary rates. And so this concept of, we need temperature as a variable turns out to be totally irrelevant, because when you work through the theory, the temperature never enters explicitly. Now you can always define an effective temperature because you have two rates, and you take the ratio and the log, and that gives you an effective temperature. The asymmetry, and you can define an effective temperature, but it can have nothing to do with the thermal temperature. And in some sense, this harkens back to the original thing with the ice ages, because it's not like the noise in the ice age situation is from nonlinear dynamics, not from not from 3-degree radiation or anything like that. Okay, anyway, but so sorry about this. I had explained why quantum stochastic resonance should be, and then I showed you that now the point of this one is to say, qualitatively speaking, it's very, very similar. This is a classical system. This is the triangles are actually from a experiment that was done on a ring laser that exhibits stochastic resonance, and you can see it all works great, but there's this peak as a function of the size of the noise, and this is all theory that we took like a two-state system coupled to a nomic bath, which was sort of trendy at the time, and said, oh, if you modulated it by driving the asymmetry of this thing, you would also get a peak as a function of temperature, because it's a thermal, these transitions are thermal, beta tail balance, they're thermal transitions. Okay, so now I'm going to tell you just a little bit about the theory we did in the 90s. And again, what we did is we followed McNamara and Wiesenfeld, where we just have these rates, and we say these rates are modulated periodically in time. And McNamara and Wiesenfeld, wrote down this model, and they wrote down, they started to solve it, but pretty early in their paper, they specialized it. And they only looked at activated rates, and they only looked at a symmetric two states, where epsilon is 0, where the two sides are symmetric. And they also did perturbation theory. And they sort of said, well, it's a nonlinear potential, it's probably hard to solve. But it turns out that, having Markovian dynamics is just a tremendous simplification, right? And so Ritva and I just sort of beat on this thing, and it turns out you can solve the whole thing up to quadrature. So you give me rates, and I can tell you anything you want to know. Okay, again, and basically I take the rates you give me, and then I put in some slides because it's a theory talk, so you can see equations, but they're towards the end. I was taught never put the equations in the beginning. But the point is you can write it all down. Okay, it's true for any rates, any value of the asymmetry, you don't have to assume symmetric, and any size modulation, it can be as big as you like. Okay, and that is, and nobody cared, just so you know, absolutely nobody cared that we could do this. Okay, so however many decades go by, you guys were all born in the meantime. And then again, last year I found out about this experiment that was Sebastian Moth and Max and Gregory were the graduate students working on it, and they're sort of first authors on the paper. And so I'll tell you a little bit about what they do, and the motivation for what they're doing is they're trying to make magnetic single atom magnetic memory. So sort of this, if you're going to make a magnetic memory and you want to make it as dense as possible, you can't do better than a single atom. And so actually quite a lot of work has gone into studying magnetic atoms on surfaces. This, by the way, is the relation to Fleet, where there's a lot of work on two-dimensional materials, and like sort of making memories and useful electronic devices. Taking advantage of the properties of two-dimensional materials. In this, we're not really going to focus on the two-dimensional aspect, but that's what motivated the work. And what they've been able to do is they have found, a system which is iron on copper nitride, where the spin lifetime is very long. Okay. And how do they know that? What they do, this is an STM tip. This is not a picture of an STM tip. This is on Sebastian's webpage, I'm sure, but and the little lines there are not real either, but you still got the idea. There's an STM tip. And then, on this copper nitride is, this is supposed to be an iron atom. Okay, and then you tunnel, and the tip is magnetized. And it turns out that the current through the STM between, you have current that flows from the STM into the sample, depends on the direction of the spin. Okay. And so you could measure the orientation of an individual iron spin with an STM using this technique. Okay. Okay, so again, this is this is the theorist's rendition of the experiment. Oh yeah, here's an STM tip, and here's your iron, and you measure the current, and then these are supposed to be the relaxation processes of what causes the spin to flip. But I'll get to that. Okay, all right. And so what happens is that, so this is the conductance. Again, the conductance through the STM. Basically the resistance between the tip and the atom, and it jumps between these values, right, when the spin flips. Okay, and this is known. So Andreas Heinrich is famous for sort of starting the development, and Sebastian is a former student of Andreas, so at least 10 years ago, but nonetheless, and so he's continued this line of work where really studying individual atoms. And again, one of the key things is that if you think about using this type of system for memory, is you want the lifetime to be long. And so over the last few years, there's been a lot of progress in figuring out how to make long lifetimes. And that means that the time scale on which these transitions happen are resolvable. Okay, you see, it takes about some substantial fraction of a millisecond for this thing to make its transitions, and so they can actually just measure in real time, like, okay, spin, are you up or are you down? And then you can watch it move. And so that's what this is. And then this is the modulated, and then there is the modulated signal, and then it turns out that a lot of the not niceness of this is due to sort of inductive and capacitive things that they understand really well. And so they're able to, with quite reasonable, quite good fidelity, figure out where the transitions are. Okay, so everything I'm going to show you after now is this, where after they've analyzed their data, we're just going to talk about, is it up or is it down? That's the question that's what we're going to answer. Okay. Okay, so sort of the fact that you could measure the spin of individual iron atoms was known, and the fact that there was a way to make it so the transitions were in this frequency range that you could resolve was also known. But what is new, and why Sebastian was all excited, is that they and Gregory, all the people, and Max, they realized that if you change the voltage on the tip, that changes the dynamics. The relaxation time of one of the states changes significantly. So the spin states have different energies, okay, and they can do this by putting on a field, but they have different energies. And to get uphill, you need to get to get from the lower state to the upper state, you have to get energy in there. And again, it's not, and in this case, it's not KT noise, but there's sort of inelastic electron scattering processes that happen, and they are strongly voltage dependent. And so they realized that just by measuring, by changing the voltage on the tip, they could control these transition rates. And that's what's new. The fact that people have been doing it by modulating the magnetic field and whatnot, but here you're just changing the same voltage you're using to do the measurement, and the frequency range over which you can do it, of course, is much more substantial. And so this is very exciting in terms of being able to do driven dynamics of individual quantum spins. Okay. So this is this is how you, as you know, this is how you get it into Glamour journal, is you make figures like this, but it's all very simple. Is that so the harmonic drive is you're changing the voltage between the tip and the sample, and then you measure the spin state, and again you measure it by measuring the conductance. You take the current, you divide it by the voltage, and then you get a conductance, and then so the drive is from the voltage with the tip, but then you just measure the current, and then you can get the spin state out in the driven system. Okay, so that's the experiment, and again it was just beautiful in my opinion. Okay, so what you can do is there are several things you can do, but we'll do the simplest thing is you can measure the rates, right? You can go from the upper state to the lower state, and that we call relaxation, and then you can measure from the lower state to the upper state, and this is relaxation, and this axis here is the voltage, right? Okay, and so there are various things you can do. One is you can measure the rates in DC, and okay, wait, hold on. I saw there's a question, Dimitri. I'm going to answer that a little later. Okay, but if I don't answer, bug me again. Okay, all right. No, you know what? I'll answer. He says, does classical and quantum hopping between the wells play together? And the answer is yes. Okay, but I think it'll become clearer later, and if not, bug me again. Okay. All right. So back to this. So the point is, you could measure these rates as a function of DC voltage, and then assume that they don't depend on voltage. Depend on frequency of the drive. But then you worry, well, what if it's heating? But you can actually, from the experiment, locally measure the transition rates. But in these experiments, that's what they did. They measured the rates as a function of voltage. They knew the voltage that they were applying, and from that, they get the transition rates versus time over a period, and everything's periodic. Okay. Oops, that's not what I meant to do. Okay, and so now now we're just taking data, right? As if I'm taking data, but never mind. Okay, but it's very similar to the stochastic resonance I showed you before, that, here the drive is at a very low frequency, and at low frequency you get, lots of transitions per period, because the transition rate is much faster than the drive frequency. Okay, and if you have a really low, a really high frequency drive, then you go many cycles before you make a transition at all, and so so you get lots of you don't get transitions every period. Okay, you get transitions only once in a while, but in between you get a situation where the up transitions, the ones from the ground state to the excited state, do synchronize with the drive. They don't synchronize perfectly, but you get a really substantial amount of synchronization. So here you see this one has one, and then this one has one. So this drive, you went up once, you went up once. This one you missed, you went up once, you went up once, you go up once, you go up once. And so, it's a really substantial amount of synchronization. Okay. So, and then the other thing that they did is they said, well, let's just try to, put a metric here, sort of like signal to noise was a metric. And so here, their metric is the synchronization efficiency. And it's just the time between the successive going ups. Okay. And what you can do is you can, just say, okay, well, this is the time between this time I went up and that time. And then here's another tau e, and you can make a histogram of all your time between excitations. And when you do that, you see a really big difference between the undriven case, the case where it's just sitting and making transitions, and the driven case. And you see you get like a really, if when you're at the when you're resonant, when you're at the right drive frequency, then you get quite a high synchronization efficiency. And so again, what they did is they said, well, between 0.75 and 1.25, what's the fraction of the successive excitation intervals that are in that peak? And it gets quite large. All right, but first I have to say that they had gotten to this. They had gotten to this. And then they said, and then I'm like, oh my God, this is, I got all excited, sorry. But like, can you calculate this? And I'm like, I could calculate everything, anything, including this thing. And this is what you get. Again, the input to the theory are those transition rates as a function of time over one period. And the output is this curve with no adjustable parameter. So it's not a surprise, because the theory is, the only assumption of the theory is that the dynamics are well described by transition rates. And when the rates are this slow, I mean, that's going to be very likely to be an excellent approximation. So if this hadn't been perfect agreement, I don't know what we would have done, but we can move forward. Okay. All right, so but now to finally see the resonance, because that was the main point of the work, was that we looked at the they plotted the synchronization frequency, synchronization efficiency as a function of frequency, and again you see it gets quite high. It gets about a third, of order one for us theorists, and when there's a peak as a function of frequency, and again, totally clear that the system is displaying stochastic resonance. Okay, so I'm so excited to be able to again, it's a theory talk, so I get to do the equations. And again, for a normal audience, I would not show these, but this is my excitement. All right, so again, what I did is that this is the McNamara-Wiesenfeld equations, right? I have I'm looking at the number of the fraction of the I pick a time relative to the drive, and then there's a probability of being in the upper state or in the ground state, and the probabilities add to 1 because it's a two-state system. Okay, so the chances that in a time between t and t plus dt I leave is the probability that I make that I come in from the ground state. So that's why I use slow and fast, because I always got, I had plus minus, and that was too confusing. So I'm going to call them slow and fast. I'm coming up from the ground state, so there's some rate at which I'm getting excited in, but then there's a probability that I'll leave, right? That they'll make a transition out. Okay, and because the sum of the probabilities is 1, then I actually have an equation in one variable, which it turns out you can solve this differential. You can write down a solution to this differential equation. All right. And so basically, if once you know that, then you can write down anything you want to know. And so this is this synchronization time. Okay, so again, this is the probability density that the time between successive excitations is some number tau. Okay, and I called it Q just out of it's the letter after P. Okay, but you can write it down. And so so the thing is, okay, there's this thing Y, which is the probability that you make your first transition from the ground to the excited state at some time relative to the drive period. Okay, and I have to tell you more about that. But everything else in this equation is just an integral that involves fast rates and slow rates. There's nothing here except for the Y, which has anything but a rate in it. Okay, so there's nothing unknown except for Y. Okay, so the interpretation of this equation is, again, it's just like you're just doing probably, if you're experienced in doing rate equations, this is not there's nothing stunning about this. It's a fairly standard analysis. Okay, so again, this quantity I have more slides about it. Okay, but this one you need to know, but it's some probability that, given that that your clock started at time t0. Okay, then you need to say, well, okay, in order to get the, because I'm doing like this transition and then I go down and I have to come back up. So I have to look at the times when I went down. Okay, and when you go down, there's this time t1 that your transition that you made the transition from the excited state to the lower state. And to make that transition at time t1, you had to not make a transition between t0 and t1. That's what this factor is. Then you make the transition at time t1, and then you go back up. And in order to go back up at time t0 plus tau, you have to not make a transition between time t1 and t0 plus tau, and then make the transition. Okay, so it's actually a extremely intuitive formula. Okay, so the only thing you need to know is the Y. All right, and it happens. Ritva and I calculated the Y in 1994. Okay, so we were sort of set to go. But we did this time come up with a sort of a nicer way to calculate the Y. And basically we noticed this time that if you know the average value of the population in the ground state, you can get Y pretty straightforwardly. And so now we really are going back to 1994, because then you say, oh, okay, well, I need the average probability as a function of time of what's in the ground state. And here's the formula from 1994. Okay, and now, okay, oh, I have to again go back. Okay, so the point was everything except for Y was just just rates. Okay. And now Y, this has a rate, the normalization, if this is, if I know ng of t is a function of the rates, then this depends on ng of t and a rate, okay? And the normalization depends on ng of t and the rate. Okay, so the question is, can I find ng of t? The fraction in the ground state is a function of time. And here's the formula that Ritva and I wrote down in 1994. And again, we defined the average rate and the deviation from the average rate, but everything in this equation is just a function of rates. So the bottom line is that we have a theory where we can, calculate, write down formulas as functions of the rates to tell you the probability distribution of essentially anything you want to know, but in particular of the synchronization function. Okay. So we were all excited that this works great, and but then I mean, you have a theory that agrees with the experiment perfectly. What's the fun in that, right? Oh, I mean, it's fun. It's fun. Okay, but the point is, you want to move forward from that. And so so one thing is actually just doing helping them to extend the ability to probe the system to frequencies that they can't resolve experimentally, because again, this STM experiment, they can resolve sub-millisecond timescales, but going much faster than that is really tough for them. And you could sort of tell because you saw the signal to noise in the signal, in the experimental data, and they don't, if they went much faster, they wouldn't be able to resolve the individual events. But what the theory does is it gives you could measure how to say it, the modulation affects the DC level as well as the AC level. Okay. And again, we were looking at what was happening on time scale of the drive, but it turns out that there is a change in the average occupation due to these dynamics, and those you can resolve. And so because you have a theory that basically takes these transitions and more or less says, look, if you tell me the rates on that time scale, we can reproduce all the dynamics, we can predict all the dynamics, you can actually get a lot of insight into what's happening on time scales that are faster than you can resolve directly. Okay, and actually in the paper, there's quite a lot of discussion about that because again, it's sort of very unusual to have a spin transition from an individual atom that is this slow. Okay, but you can then extend, by using the theory, you can sort of extend your ability to find out what's happening with these rates and these inelastic electron scattering processes into the regime where you can't resolve directly. So this one is sort of written as if it's the future, but they've actually done quite a lot of work on these lines. Okay. Oh, and then the other thing that they're working on right now is that you can do this looking at systems with more states, and again, one of the things that they're doing, which I think is very interesting, is to look at interacting. You can put two atoms in there, and now you have more states, but you can still write down a rate equation, a transition rate formalism for it. And there you're not, as far as I can tell, it's not going to be possible to do this in a complete analytic description, but still the fact that the Markovianness of the description simplifies things enormously. And so that is actually something that they're really actively doing right now. And then something which I think will be really interesting for the future is that, again, this question of the fundamental dynamics, okay, that again, the only thing the only assumption that is made in this theory is that the dynamics are Markovian, okay, and that means that, like, if you're in the state, there's and you fix the voltage and you fix the value of the drive, the probability that you're going to leave in the next increment of time. But that could depend on history. And I think if we think hard enough, we'll be able to come up with a way to really probe the time scale on which the dynamics become Markovian. And there, I think that's could be a really interesting thing to do, because this kind of system is expected to have some polaronic effects and sort of the coupling to the ohmic bath. You do get long time scales coming out, and this provides, I think, a window to be able to probe them. But I think there's a lot to do, because again, this is just the first observation, and the fact that we can really say a lot about experiment, I think is really useful. Okay, but now let me go back to Dimitri's question. Okay, okay, so Dimitri has two questions. Okay, so the classical and the quantum hopping, I mean, hopefully it was clear that, you put in rates that, okay, so quantum, right, you're coming in, and it's sort of, if you think about the fast rate, it's coming in as a function of temperature, but again, the fast rate could be doing whatever it wants to do, and the theory still applies. And in that case, you cross over more or less to something that looks very much like classical stochastic resonance, as opposed to quantum stochastic resonance. Okay, but then you run into this issue that you don't have that same, at some point, new physics comes in, and then you don't have the two-state transition rates independent of history thing. But that's in some sense the where it breaks down is sort of this Markovianness of the transition and the number of states that you have to include. Okay, are interactions important? Okay, so again, what's happening here is that you're not measuring electrons, you're measuring spins. Okay, so you're measuring a macroscopic current. I mean, for these guys, it's macroscopic. For you and me, it's not. But you're measuring the tunneling rate of electrons from the tip going into the atom. And so you're not measuring one electron, you're measuring a whole pile of electrons. And again, the issue is that like those electrons that are doing the tunneling do perturb the system. And that's the source of the noise that's causing the transition. Okay. And in some sense, that was why if you talk to some people, they were worried. They'd say, well, but it's not thermal, but again, if you go back to the original stochastic resonance, that wasn't thermal either, right? But the point is that the electrons that are tunneling are measuring, and they're also perturbing the system. But as long as you assume the time scale in which they're doing the perturbation is super fast, so that they're sort of like, whatever it's going to do, it's already done it before you've made your next transition, then the theory should apply. Okay. So so again, it's not that there's one electron, it's because there are so many electrons that it's statistically, you've hit some statistical steady state. Okay. Okay. And I think, wait a minute, yes. Okay. I did want to say one more thing about the multiple states, is that Sebastian has some other, is studying that now. Okay. Okay, so just to summarize, so first, if you didn't know about stochastic resonance, now you do. That noise can enhance the synchronization of a system's response to an external drive, and it does occur in this quantum system of individual iron spins on this particular substrate. And again, because it's a theory seminar and I'm a theorist, I gave a lot of love to theory, where you describe the dynamics using time-dependent transition rates, and you can predict the dynamics and basically any quantity that you want to calculate. And then there's a little bit to say that you can then actually probe timescales faster, because you modulate on a fast timescale. So even though you're measuring slowly, you have a way to connect the fast and the slow. And we're working to extend to complex systems. Okay, so here's a question. When I say Markovian, do I mean this in the classical sense, at the probability level? Well, I mean, I guess the easiest thing to say is, here's the equation, right? Okay, and the idea is I didn't write it on the slide, so thanks. This W slow and W fast are prescribed periodic functions of the drive. Okay, they don't depend on anything else except for like what state you're in and where you are relative to the drive. Okay, so I mean, in some sense, it is in the classical sense, right, that I have a transition rate that doesn't know anything except where it is now. Okay, that's my understanding of Markovian, right? It's not a rate and state, like, but if it was a thing where, like, if you think about a Polaron effect, if you have a particle and there's like some bath, you can have the thing, you make the transition, and then you have to, a cloud forms, and there's some time it takes for the cloud forms, and after the cloud forms, the rate goes down, because it's sort of, it's like a seat cushion, right? You go in and the ball would roll off, but then you've made a dump, you've made a depression for it, and then it stays. Okay, so that's what I mean by Markovian. It's just that these rates here, this rate is prescribed. Okay, it's not anything that independent of the configurations of the ends. Okay, that's what I mean by Markovian. There's no memory of the past. It just knows where it is now. And then you told it what the transition rates are, and so that means it knows where it is now, and given where it is now, it has a probability of going to the other place that depends on nothing else except where it is now and where it is in the period. Okay, so that's what I mean by Markovian, which is I think fairly standard, but again, the fact that things are depending on time in this external prescribed way, I think of it as still Markovian. So there's an explicit time dependence, but it's sort of the most trivial imaginable. Okay, so I think I was done, which is good because my time's almost up. And yeah, I just want to thank you for your attention.
Can you hear me? This is Mary.
Yeah, I can hear you.
Good.
I can't hear David.
You can or you can't?
I cannot.
Oh, it seems to have dropped out. I'm not sure. Were there any other questions from the audience?
Oh, here.
Oh, yes, here we go.
How many independent parameters are in the simulations? Oh, can you have him, can you make it so he can talk? Because I don't know which simulation he's talking about.
Let me have a look. Dimitri. Yep, there we go.
Okay,
Hello,
so you can now just ask, because I don't know what, yeah, okay.
do you hear me?
Yes.
The question is, first of all, thank you for a very nice talk. And the question is, you have these transitions rates, the omega, that are slow, fast. So
Yeah.
how do you choose them, and
Oh,
how many parameters are needed?
yeah.
And are they
Okay.
connected to how many parameters are needed to feed the experimental data?
Yeah, okay. So what they did, again, and I think the way to think about it, you don't have to do this, but this is what they did, okay. They measured the transition rates, from the lower to the upper and the upper to the lower as a function of voltage. So if you look down here, this is the voltage that's applied, and that separately, well, actually, I think if I go back to here, okay, here's the occupation of the excited state in DC as a function of that voltage, that very same voltage. And because of the detailed balance, I mean, you can get out the rates. Okay, so that's one way to get this. So this is measured, but in a separate experiment.
I see.
Okay, then then this is fit to Fourier series, some small number of. We ended up, everything is done using Fourier expansions of everything. Yeah, but this is the input. Okay, which again you get from a separate experiment, and then after that all you do is integrals.
Okay, thank you.
Okay.
Okay, is my microphone working now?
Yeah. Okay.
Sorry about that. I got a message saying my microphone wasn't working and to plug it and plug it back in again. So thank you very much, Susan, for a really, really interesting talk. I wanted to ask you, is there any dependence on the functional form of the noise that you're applying, depending on the, if you like, the effective Q of the quantum system that it might be interacting with, for example? Or?
Oh, I see. Not in this regime, because I mean, so one way to think. Okay, so when I got it, now I can tell you more about my youth when I got into the business. So there's sort of two separate regimes that you can think about, limiting regimes. So the one is that you have energy levels, and you're doing transition between energy levels. But you can also have a situation where you sort of have, I mean, and if I'm thinking about an atom tunneling, this I got into it because I was working on two-level systems and glasses. Okay, and you can think about energy levels and doing transitions, but that's not the way to think about a lot of these problems. In this one, you can be in position eigenstates, or in this case, I can have a superposition of up and down, but here it's up or down, and basically you're measuring it often enough that you should think about being in those eigenstates, not the quantum eigenstates, but the classical eigenstates, and then you're tunneling between them. Okay, and in that case, and so the way I think about it is the bath is measuring this thing. Okay, and what the bath is doing is it cares about what the is the spin up or is the spin down, and so it's constantly the spin wants to do something else, but it's getting measured often enough that it's stuck in one or the other. Okay, so it doesn't actually, so that's why any of the details of the noise don't matter, because it basically, the noise is measuring it faster than it could ever make a transition. So you just don't, you're not sensitive to any of the details because it happens so often. You see what I mean? And so that's why it's such a strong constraint that the dynamics are Markovian, because all of the possible complications, of which there are many, that could happen, the system has forgotten them, and it just starts again from scratch. So It's like Groundhog Day, I guess. Every day it wakes up, it's the same. But yeah, but that's why the details of the noise don't matter.
Is there a sense in which the if I have a two-state system with a characteristic frequency, think of a Rabi system or something.
Yeah, okay.
And I'm slightly detuned, and then I introduce noise. Does the noise have the effect, therefore, of effectively retuning the system to some extent, or how does it affect the dynamics of a system like that?
I see. That's interesting. That's a really interesting question. Because I've been, I think about, oh, they're energy eigenstates. That's my right brain. And these are position eigenstates, and they're my left brain. But I haven't really thought about that process, trying to generalize that process to the case you're saying. I mean, the worry is, okay, here, if you think about, I think I'm going to talk about it in terms of spin precessing, okay, that, the limit I'm talking about is like this, nothing happens, right? And you just have this possibility of, banging it, okay. But here you have, in this other case, you have a situation where you're processing, okay? And then you worry about like when you hit it, it depends on where you hit it relative to where it is in its cycle, okay? And that leads to complications, but on the other hand, it's not out of the question that you could average over that. And so the real answer to your question is, I don't know. I mean, except to say I've only thought about this other limit, and I'd have to go away and think before I said anything.
Yeah, and one of the reasons that I was interested in that was, if you think about, building a quantum register from a set of n qubits and so forth, and there is there's a spread, for example, in the characteristics of the qubits. There might be quantum dots, or there might be Josephson functions, or something like this. And then if you're driving that like with an external drive, which is a given macroscopic external field, for example, it won't necessarily tune equally to all of those quantum systems. And so the register is maybe a bit hard to sort of manage and to control. But perhaps the introduction of noise would decrease the sensitivity of the spread of those qubits forming the quantum register to this external drive field. So that was one of the things that was motivating the question that I was asking, whether or not that this could be used for that purpose.
It's a really interesting idea. I because I've done work on, trying to mitigate errors, and it's been much more of the, well, let's try to mitigate the errors. And it's a really interesting idea, and I don't know the answer, but I'd have to get back to you on that. You had to come up with something specific, but I hear you, and it's an interesting thing. I mean, I will say the following: it's just the requirements to do quantum computing are so stringent that sort of this, oh, it synchronizes half the time. I mean, that compares to 0%. But when you're doing quantum computing, everything's like 99.9, and so it would have to work really well.
Yeah.
You know what I'm saying? So, but that's a minor, that's a minor thing. And I'm embarrassed to tell you that even though I've worked on that problem, I never thought to apply stochastic resonance to that problem.
Well, thank you very much, Susan. I don't think there's any more.
Yeah, there is one.
Oh, there is.
Okay.
Question here, and I'll just allow Augustine to talk. So.
Okay, great.
Are you ready?
Hi, can you hear me?
Yeah. Hi.
Hi, Susan. Thank you for the nice talk. I have a naive question that maybe I missed. So, in this prospective case of a n-state system, so beyond states, wouldn't you think that the processes might become non-Markovian? Because now I have a very complicated pathway from one state to the other.
Yeah, well, no, you're absolutely right. Well, let's put it this way: it depends what you mean by Markovian. Sort of, it depends.
So, based on your definition.
Well, I mean, the thing is, I mean, in some sense, this is what makes it super interesting. Because I'm sorry, it was a value judgment, but still, The thing is that there's this thing of like, there are many different ways to get to a given state. And so you won't, and it won't be nearly as simple, that's for sure. But the thing is, you can still have a situation like you're in that state, and given you're in that state, your chances of getting out of the state and the transition rates to all the other places you could go could not depend on how you got there. And in that sense, the dynamics would be Markovian, but they would still be much more complicated than this two-state thing going back and forth, obviously.
Yeah. But your hence implying that your formalism could still be applicable.
No, that's what. No, I guess what I'm saying is that the formalism is dead. Is it can't it can't possibly work. Because I mean, you never say never, but it was actually a lot of work the first time, and once you have more, and this is known in the classical context because there's a whole little industry lit of what are called predator-prey models, which are sort of very similar to this, and you can get really complicated behavior. So the analysis won't go through, but this idea that making the Markovian approximation will simplify the problem to a point where, because then you end up at fixed points, for instance, like there are like some pretty strong theorems of, if you have, Markov chains, they converge. And so I think you could get somewhere, and that's where the interest is, because, but this theory is not gonna, I just can't imagine that once you have three states that you can solve it all analytically. I mean, because that's essentially what we have, right? We just have, we have integrals, I mean, that's not gonna happen, but you still could get really significant simplifications. You see what I mean? Because, there's a lot of dependence that you're leaving out.
Okay, I see. Yeah, thank you.
Okay.
David, there is one more question if Susan has time to answer that. Hello?
Yeah, hello, I'm still here.
Oh, good. Victor Flambaum has a question.
Oh, okay.
Are you there?
Yeah, can you just talk? Oh, wait, can I? No, I don't. Yeah, there you go. You can talk, Victor. Hi.
Yeah, it's a question because you mentioned quantum effect. And in principle, noise influences quantum probability of a tunneling.
Mm-hmm.
Yeah, was it included somehow in your consideration?
Yeah. So now I can tell you about these. So that was like the whole point of the work we did in the 90s was we had just done, I have a talk from 1994 I can give you that was exactly on that, of what the rates do of a quantum system. It was, well, I'll just talk, since it's my youth, I can talk endlessly, but so what it was there was an experiment done by Brage Golding and Neil Zimmerman, and they were using universal conductance fluctuations, where basically you'd have an atom. It was in bismuth, and bismuth is good because as you make thin films and it's conducting, but very badly. And so then the atom would move, and universal conductance fluctuations amplified that, so that the conductance change when one atom moved back and forth was measurable. Okay, and there you could, so this again was the motivation of the work that Ritva and I did. So what you could do is just measure the resistance as a function of time, and you could watch, the atom going back and forth. Okay, and so there you could see the effects of the bath. You could measure the transition rates as a function of temperature, and it turned out that the asymmetry depended on magnetic field. So you could vary the magnetic field and the temperature, and you could explain it all in terms of the coupling to the bath and those effects. So in those days, it was, we had an experimental system where it was thermally excited, and we had sort of a theoretical understanding of the origin of the rates. Now here in this system, they do have actually quite a good understanding of theoretical understanding of the origin of rates, but it's quite non-equilibrium process. And And again, it really is, it's like they just calculate all these different inelastic electron scattering channels, but they actually have a quantitative, they have a quantitative understanding where the rates are coming from. But these sort of polaronic effects, like the Anderson orthogonality catastrophe, plays an important role in the individual atom tunneling back and forth. But in this case, you're not in equilibrium, and so those sort of equilibrium concepts are less relevant because again, this voltage tip, and again, the voltage isn't so high, but it's really close, so the electric fields are huge. So but I'll tell you what, someday we'll see each other in person again. So it looks like it'll be next year sometime at this rate, but we should talk.
Yeah, because it's a complicated question actually.
Yeah.
If you have simple problem, you have quantum tunneling, and there is some noise. How amplitude of tunneling depends on this noise. I know that Leggett did some work on this.
Yeah.
We did work on some quantum fluctuation effects, like radiative corrections to quantum tunneling.
Oh, well, we should talk. I mean, again, this is in the super overdamped limit is where we think we are, but we should talk because I think the same question of like, when you have a more coherent quantum system, how do these things generalize? It's something I haven't done at all. And it's you would have thought I would have thought about it, but I haven't. And so we should talk.
Okay, thank you. It's complicated. Maybe it's not the right place to discuss. Thank you.
Okay, yeah, no, someday we'll see each other in person, but not soon.
Okay, thank you very much.
Yeah, thanks, Victor.
All right, I think I'm safe to say there are no more questions.
Yeah. Feel free to
you.
send me an email if not. Okay.
So thanks very much, Susan.
Thanks.
And,
thanks.
I just remind everyone that this talk will be uploaded to the Australian Institute of Physics YouTube channel. So if you want to watch it again, it will be available for you there. Thank you very much for everyone for attending, and we'll see you at the next seminar.
Great. Thank you.
Bye for now.
Okay, bye.